So much for the invitation. Okay. Thank you so much for the invitation. So I'm going to start with a little bit of manifold theory. And the story begins with a fairly innocuous question, which is how can we tell whether or not two manifolds? And for me, manifold here is going to mean smooth, compact, and let's say dimension at least 6. And we're asking when are two manifolds diffeomorphic? And here's a basic strategy for proving this. So first, you start with some manifold here. Here's M prime. And you can first try to construct a cobordism between them. So cobordism here is just it's just a manifold of one dimension higher whose boundary components are M and M prime. And let's call this N. And if we can show that N instead is diffeomorphic to M cross I, we win. And that's because the diffeomorphisms are given by either side of the cobordism. Okay, so there's actually a full answer in the simply connected case. So this is a theorem, the H-cobordism theorem. Due to Smale, if I remember correctly. And it says that if M is simply connected, this implies that every H-cobordism is trivial. And H-cobordism here means the inclusion is homotopy equivalence. Okay, awesome. When pi1 of M, can you still see if I write down here?
Yes.
Okay, awesome. If pi1 of M is non-trivial, there's a single obstruction, and this is called Whitehead torsion. And it lives in a fairly interesting group, which is the infinite general linear group of Z pi1 of M. And you take its abelianization and just mod out by whatever you have coming from the fundamental group. Okay, and the way to think about this is that the commutator subgroup is going to be just diagonal matrices. So this group is more or less addressing the question of whether or not you can diagonalize a matrix. And this group goes by another name other than the Whitehead group, and it's a quotient of the first K-theory group of Z pi1 of M. Okay. And in fact, elements of this group are in bijection with H-cobordism classes of a given manifold. So here's a more sensitive question that one could ask. So when can we specify the diffeomorphism, i.e., if we find a trivialization, oh, sorry, my handwriting is getting weird. When can we say that this identification is unique? So this is a question about, all right, so we find some diffeomorphism, but can we just say that we found the diffeomorphism obtained from this procedure? And the answer to this question is given by pi 0 of diffeomorphisms of M cross I fixing the bottom. Right, so this identifies diffeomorphisms up to isotopy, right? And this thing is called the pseudo-isotopy space. Okay, awesome. So the way we should think about this is a pseudo-isotopy is something on M cross I, and all these things are going to be diffeomorphisms, but they don't have to respect the level set, right? So you look at these certain levels, and these pseudo-isotopies can like bend and warp. Whereas if we could strictify this, like straighten all those layers, we would just obtain a genuine isotopy. And that's because the restriction at every step would just be a diffeomorphism of M. Okay. So this is a space that we're very interested in. And kind of amazingly, these kinds of calculations get you pretty far. So here's a theorem of Cerf. And it says that if M is simply connected, then this implies, maybe I'll write it like this. Then pseudo-isotopy implies isotopy. Okay, so these methods can be actually pretty good. And this space, as you can imagine, is very difficult. All right, first of all, are there any questions so far? Okay, awesome. So this space can be very difficult to compute with, but there's a kind of another amazing result called Igusa stability. It tells us when we can get a pretty good handle on this, and it's going to be a stable range. So there are these maps that we can obtain. M cross I, and we can study what happens to these. So I'm going to write the pseudo-isotopy space like this. And we can study what happens here. And what Igusa tells us is that this map is K-connected. And the dimension of M is large. So the basic principle here is to just increase the dimension of M by successively crossing with intervals. So what we can do is we can just take the union of all these spaces, where we take HK of M to just be defined as the H cobordism space of M cross I to the K. And if we can understand the homotopy groups of this space, it sheds light on the homotopy groups of the usual H cobordism space in what's called the stable range, or the Igusa stable range. Okay, so I'm going to call H infinity of M the stable, let's say pseudo-isotopy space. Okay, and now we can understand how K-theory enters the picture. So it turns out that when M is a smooth manifold, there is a cofiber sequence that looks like this, where A of M is going to be the A theory of M, which is the K theory of a certain category, which I'll tell you about in just a moment. And it goes to a space called the Whitehead space. And the Whitehead space has the amazing property, and very importantly, when you loop the Whitehead space once, this is homotopy equivalent to the stable H cobordism space. And this is called the parametrized stable H cobordism theorem. So if we can understand the algebraic K theory associated to M, that means that we can start really understanding these stable H cobordism spaces. Okay, so A of M is, so if you're used to thinking about algebraic K theory in terms of rings, what you can do is take loops M and take out the algebraic K theory by your favorite construction, or alternatively, you can look at its suspension spectrum, and that won't change the K theory. So this is kind of, we think of this as like S that join loops M, which is a sort of like, they call it spherical group rings, because this is an analogy with the sphere spectrum replacing the integers and pi 1 of M replacing the loop space. So this is like a space level lift of whatever the algebraic K theory was originally. So let me tell you what this construction looks like on pi 0, and I don't think I'm going to go into this kind of like ring or stable perspective. So what one does is you take M and you look at, let's say, finite spaces over M, Y, and these are just spaces with a regular map to M, but also a section to this map. So we think of M as living inside this space, and you're attaching, let's say, finitely many cells to M. And then what pi 0 of A of M does is this detects all these spaces, but whenever there's a cofiber sequence, let's say to Y double prime, it enforces the relation that Y prime is equal to a formal sum of Y plus Y double prime. And I think the sort of motto here is that the higher homotopy groups of A theory detect things like automorphisms, right? So if you can realize Y prime is say, attaching finitely many cells, and y double prime is attaching finitely many cells, then this remembers the way in which you attach them. And that's why this is a more sensitive invariant. Right, like it would be really surprising if all of this data just depended on a pi1 condition. So the way that we get a handle on this space is via something called linearization, or one way to do it. So K-theory is already horribly difficult to compute, and this is just making it even more difficult to compute. But there's a map that goes from the A theory of X to the K theory of its fundamental group, and it has many desirable properties and shows up in many theorems. And basically, this is just a comparison map, right? Like, before we were computing the K theory of just a ring, and now we're computing something like the K theory of a space.
Uh-oh.
Any questions?
We lost you for a moment.
Oh, can you hear me
so
now?
yes, we can. Can you repeat that last bit, Andres?
What's the last thing I said? Oh, there's a linearization map from A theory to the K theory of Z pi 1. And the idea is to test the non-triviality of elements by their image. That's all I said. Okay, well, I can pause now for questions if there are any.
Which Igusa is responsible for Igusa stabilization?
Oh boy. I should know this. Maybe Roshi. I'm just gonna Google it.
Is it Kiyoshi?
Yeah, I think it's Kiyoshi as well. That's correct. And by think I know, I looked it up. Sorry about that. And you refer to people by their last names for so long, you forget that they're like actually just people. So yeah, maybe that's pretty embarrassing. Okay, so let me just say a word about how this linearization works in spirit. Oh, I already told you this. Okay, there's one additional fact that I neglected to mention, which is that in the case where your manifold is smooth, there's actually a section to this map in that cofiber sequence, and A theory, in fact, splits as the product of these two spaces. This is something that's still not known equivariantly, and it's something that we've been like actively working on. Okay. Back to the story. So here's how linearization map basically works. You start with something like a space over X, and what you assign to it are chains or relative chains like this, which we're entitled to do because there's a section. And it's kind of amazing that when you impose a certain finiteness condition on Y, say it's a retract of a finite CW complex, which is, I think, as general as you can make it, this is not just any old chain complex. Oh, and I should probably say where it lives. It lives over Z pi 1 of X in this case. And actually, we can do better than that. It actually lives in, it's a perfect complex. So it's the type of thing that's finite enough for us to take its K theory. If you don't like this, you can replace what I just said by there's some version of an Euler characteristic that picks out a projective module for you. And that's, I think, how, for example, Wall first imagined that this kind of thing would work. Okay, and this map is coherent enough so that it induces a map from the A theory of X to the K theory of Z pi 1 of X. And this is the non-equivariant linearization map. And now I will begin the equivariant story. Okay.
Excuse me, what is tilde over X and Y? Is this the universal coverage space? What are
Yes,
the tildes?
yes, those are the universal cover spaces. Okay, any other questions before everything gets messy because groups enter the picture? Okay, awesome. Let me make a little warning here, which is that I'll be focusing on one part of the story, but there's much more to say. Namely, for those in the know, I'll be focusing on fixed points of all the spectra we care about. on genuine spectra. But this whole story lifts to genuine G spectra. It's just not really a fun thing to talk about in general. Okay. So the first thing is that Kari Malkovich, hope I spelled that correctly. Maybe the I got transposed. Oh no. I think so. Merling. That's Mona Merling, my advisor. Showed that for G a smooth manifold, oh, what did I just say? M a smooth G manifold. We have a co-fiber sequence that looks like this. And moreover, this spectrum, also when you loop it once, is the stable G H cobordism space. So this story that worked non-equivariantly ports over completely. So let me just mention, this is basically the reason that equivariant A theory was constructed in the way that it was, and it's due to a fact of stable equivariant homotopy theory, that when you take this whole sequence, so I guess I can copy it. You take this whole sequence and append G fixed points everywhere. Then Tom Deek showed, classically, so this is due to Tom Deek, that this thing splits into something maybe confusing on first sight, but hopefully I can say more about it. So this is to say that it splits into non-equivariant suspension spectra, but you replace the spaces with the H fixed points of your manifold, and then you take something called homotopy orbits. And I'll say more about that in just a moment. And then A theory, likewise, and this is a weak equivalence, also has a splitting. And it was basically cooked up in order to have this splitting because they wanted to map from this equivariant suspension spectrum to the A theory. So this is the non-equivariant A theory of MH, HWH. And there's a map here that's compatible. Okay, so let me say a bit more about what these objects are. So by WH, this is the vol group, and it's defined to be the normalizer of H, modulo H. And we can think of this as the residual action on fixed points, or that's how I think about it, or as automorphisms of G mod H as a G space. So that's just the finite set. And we think of M, H, H, WH. So this is just literally defined to, or one definition of it, cross MH, and you mod out by WH. And the idea here is that you want to replace, so the action of the vol group might not be free, but you want to replace it with something where the action is free, and then take the quotient. And this is how you get something kind of coherent. Okay. And I should say a bit more. So all I've said is that there exists some co-fiber sequence. It has connections to the stable G-H cobordism space, but I haven't actually said what we're taking the K theory of. And what we do is it's exactly analogous to the non-equivariant story. The G fixed points of this are just like the K theory of G finitely dominated G retractive spaces. And finitely dominated means retracts of finite CW complexes. And retractive means that it has a section over it. And then you get this splitting. And the source of this splitting is basically that we can look at retractive spaces over X, where for this map, the orbits of G acting on Y minus the copy of X sitting inside of it are all of the form, or I guess I can say are all homeomorphic to G mod H. So you're filtering basically by isotropy types. And it turns out that in this story, taking the K theory of these subcategories just turns out to be, or let's say A theory, is weakly equivalent to the A theory of XH, HWH, and retractive spaces over that. Okay. So let me get to some of the more out, any questions so far? Okay, awesome. Let me get to maybe some of the more like of the algebraic perspective here. So it's a classical theorem of Elmendorf. That G spaces where F from X to Y is an equivalence if it is on all H and G. That's basically a definition. And functors from OG up, where this is the orbit category. So this is just the category where every object is G mod H and the morphisms are equivariant maps into spaces. And so what we were trying to cook up is basically we were trying to take this perspective and construct an equivariant linearization map using these ideas. So let me talk about some classical work. And by classical, I mean from the 90s. This was done by Wolfgang Look, Paglivo. They all have different, mildly different versions of this, but they all amount to the same thing. And possibly some others, is that they cooked up this element that should be, this should be living in pi zero of whatever like you're trying to figure out what object should be a receptacle for linearization. And what they said is that there's some object that's usually related to K0 of something. Non-equivariantly, it's pi zero of the K theory of the fundamental, of the group ring on the fundamental group. And they said that it was in some giant space like this. In the K theory, or let's say K0. H, but you took a semi-direct product with WH. And this looks awfully similar to the Tom-Dieck splitting, but this term on the right doesn't have a very good interpretation, I don't think. So what we wanted to do is we just made a somewhat mild observation that we could, instead of looking at things like this, try to lift this whole story to spaces. So we know that there's a fiber sequence like this. Oh, and I should put it here. The BWH, where BWH in this context is just, let's say it's a KWH1 space. So any space with the free WH action whose universal cover is contractible. I think I just said that. Okay, and we have this fiber sequence, and if we assume that the action is pointed, that actually gives us a little section here. And if we just pass the pi 1, so we know that pi n for this guy is equal to 0 for all n greater than 1. And so we get a short exact sequence that looks like this. I1 of X, H, W, H. And we have a section here. So in fact, what we're seeing is that on fundamental groups, this is just a version of that twisted group ring. So Z of this whole thing should just be Z adjoin pi 1 of X, H, twisted by this WH action. Okay, so now this is really starting to look like the Tom-Dieck splitting, and there is a kind of approach that one could take, which is you look at this up here. Oh, sorry. Okay, I messed everything up. You look at this object over here. And now you can just do the Tom D splitting pointwise, right? We know that the A theory of X when X is a G space splits in the same exact way. So you could just level wise do the linearization maps, and that would be maybe an adequate linearization map. But the problem is that this is like a fairly uncomputable way to do things. And so we wanted something that didn't really rely on this. So something you define a priori and then show that it has such a splitting.
Sorry, should it be concerned if like the fixed point spaces aren't path connected or something like that?
Yeah, sorry. Yes, I should assume. There's a version that you basically just index it on the path components, but for simplicity, yes, let's assume everywhere that MH is connected for all H, just so I don't, it's more notation, but it's the same idea.
Okay.
Okay. So the way that we decided to do this was just motivated by Elmendorf. We took a guess for what kind of object we should be taking the K theory of, and then we wanted to show that it had the desired splitting. So since X is known as a pre-sheaf on the orbit category, well, we just figured we should be taking things like functors from OG into ring. And the assignment here is basically that we just send G mod H. And we took a little bit of work to figure out, for example, what the projective or perfect modules over things like this looked. But barring those kinds of conditions, this is really just what should be the receptacle for any linearization map. And how much time do I have? Oh, I have time. Okay, cool. So what we showed is we just made a definition and a coefficient system of abelian groups. It's just something like, and we wanted to figure out what the monoids were in this category, and these are exactly just as we wrote above. So this has a symmetric monoidal product, and that product turns out to just be a pointwise tensor product. And so what we're looking at are, we really ought to be looking at these guys. And it's maybe worth mentioning that this almost never happens, because this is just dumb luck. Okay, so now we should think about, well, what does a module over something like this look like? So to do that, I need to introduce one more object called the twisted group ring. So we could take any, so when is M? Module over R. And the answer is not when it's pointwise a module, but that's pretty close. So this is maybe a lemma. This is a module. So this is kind of a weird looking object. These are called twisted group rings. When the action of, like if this were just a constant ring, then this would amount to just taking group rings level wise. And the trick here is basically that you always have a residual action by this vol group, and you need to account for that to be a module over this whole thing. Namely that objects in G mod H have automorphisms. But there's a different way to think of modules over this. This is basically just the exact same S and R G mod H module with a semilinear G action. And that's just to say that if you act on something like RM, then this should be the same thing as you just act on R and then take GM. So if you want to pass this action through coefficients, you need to take the action of the ring onto the account. Oh, sorry, this should be, oh, okay, I can fix this. Okay, cool. Any questions? Okay, excellent. And then, okay, so we can take the K theory of this whole guy. Right? Or you can take perfect chain complexes. That's no problem at all. And we just define this. This turns out to be the same thing as the G fixed points of the full object that we defined. So I'll call it genuine. In analogy with the G fixed points being the K theory of G retractive spaces over X. Okay. And so the main theorem is that this sort of naive guess actually does have splittings of the desired type. So the theorem says that R G is weakly equivalent, the product over conjugates and classes, R evaluated on G H. So it splits as a product, and maybe this is a kind of weird way to think about it, but the main example slash corollary is that if we take the following coefficient system, then we can look at what this splitting does. So now, K theory. And it's just the fact of algebra that this is in fact the same thing. Ooh. WH. And this is, of course, what we desired because this is equal to Z adjoined pi 1 of X. HWH. And the way we typically think about this is on the level of spaces. These guys play the role of twisted group rings. For A theory. Okay, awesome. Okay, now we can write down the linearization map before the splitting, and I'll say exactly what it does, and it's exactly an analogy to the non-equivariant case, which made me very happy. So here's a theorem. Oh, and I should have said earlier, this is all joint with David Chan, everything I've said today, and Maxine, who's here, which is embarrassing. So here's the theorem. Well, we can take G retractive spaces over X. And all we have to do is define a map that takes us to chain complexes here. And it turns out that these, in fact, are just, these are modules over the twisted group ring. And they have the requisite finiteness conditions. And we can make an assignment with this. And so what that means is that this entire chain complex, so this is at level G mod H. So maybe I'll write it like this. But when you do it everywhere, what you're obtaining is a map from few attractive spaces over X to modules over what I defined earlier to be Z pi 1 of X bar. And actually it's incorrect, so it's fine. Okay, nice. And so what are the main properties of this linearization map? Well, the first and most important one is that it's compatible with splittings. Oh, and this is only on the level of G fixed points again. So by compatible with splittings, I mean that when you actually do the splitting, this restricts to the usual to a linearization map from the A theory of XH, HWH to the K theory. Oh no, I ran out of space. But basically, or maybe I should have written this differently. Sorry. Let me try that again. Which is very good because that's, I mean, if there's a linearization map, it has to be this. And these things imply, for example, that the linearization map is an isomorphism on pi 0 and pi 1. And by that, I mean for all subgroups of H when you take the H fixed points. It's the fixed points of this thing also give the usual K-theory invariants. So things like Whitehead torsion and wall finiteness obstructions. And so many of these K-theory invariants also end up living here. And they're usually defined in terms of the splitting, but in fact, there are usually lifts of these to like the actual equivariant story. And when you look at the splittings, you recover them. Okay. And the last thing, which I think is maybe the most important to me, is that this linearization map is not harmful to the soul. Like doing it after the splitting, I really didn't like that. It was a very upsetting fact for me. Okay, how much time do I have left? About 10 minutes, is that right?
Yes.
Okay, awesome. So I'd like to mention how this story actually soups up and talk about some ongoing work. And this time I'll cite everybody. So here's some ongoing work. Hopefully coming out soon. And this is joint with Maxine again, David, and Anish. Okay. So the thing to realize is that we did this for fundamental groups, but in analogy with the non-equivariant story, we should actually just lift this whole thing to the level of spaces, right? Like there's nothing stopping us from just making a definition where we have functors from G mod H, and what these go to are, sorry, 1 second. So I'm going to write it as the spherical group ring. And kind of importantly, this is on the inside. And by this, I just mean the suspension spectrum. And what I'm defining for you basically is just a map that it doesn't land in discrete rings, but it instead lands in E1 rings of spectra. So just rings in spectra, or if you like, just loop spaces, so you can talk about modules or things with loop X action. And this is kind of like a more algebraic approach to defining it. Like you take the category of perfect modules over it, take its K-theory as one usually does, and that recovers that story. And in fact, what we're seeing is that if we take objects like that, so we're thinking of these as coefficient systems in spaces or in rings, then this actually gives light to a new kind of construction where we could have just done this the whole time, right? I'm going to write it like this. And by that, I just mean every level you do fixed points. And so this is kind of nice because we can also reinterpret our linearization map as something like a pi1 map. So it's being induced. Maybe I should write this better. By something like this, when you think of both of these as coefficient systems of rings. And moreover, what the reason that we're doing it this way is because we can actually test this against other invariants. And as I said before, what we really want is we want a splitting in the case for modules. So what we want is we want a statement of this form. And to do that, we have to construct the section. And the way this section works classically is that you take the A theory of X. So classically, you can take the A theory of X. This always has a map to the free loop space on X. Oh, that's old school. I don't think people write it like that anymore. And then you can choose a base point, and the evaluation map here gives you a map back down to X. And when you view all these things stably, that gives you a map, that gives you a section to the map from the suspension spectrum of M to the A theory of M. And so the reason that we're considering these types of models is because this thing has an algebraic interpretation as well as the topological Hodgkin homology of X. And using this kind of technology, these like pre-sheafs of E1 rings, it also it begs for a definition for THH of G space as well. And this is basically the model that we've been using, and our hope is to actually prove that one can repeat this story equivariantly and obtain a splitting in the equivariant stable parameterized H-cobordism theorem. Okay, I think that's everything that I wanted to say. Thank you.
Do you have any questions, comments for this?
It is in this last bit, is the obstruction like defining a G equivariant version of the trace map to some version of THH?
So that's not an obstruction. Well, okay, so first of all, you could always cheat, right? So the proofs of these splittings don't use much about K-theory at all, just the fact that it's additive, basically. And THH also satisfies this property and therefore has the same splitting. So one could just do the trace map after the splitting everywhere and just check that it commutes with the way you actually split it. But you could alternatively just define this THH, write down these sort of like equivariant trace maps in the same exact way, and then yeah, like obtain it that way. So writing down the trace map is a bit of a sensitive issue, but hopefully it's not the big obstruction. I don't know which part I'm worried about the most. I hope that it's going to work. But one benefit of this kind of approach is that it gives definitions, or I don't claim that they're the correct definitions, but as we've been doing like this whole time, you're basically just trying to use the non-equivariant theory to obtain equivariant invariance. And I should say that like this kind of approach definitely makes it a little bit easier to see how to define THH.
Any other questions? Let's thank Andres again.
Thank you so much. I don't know if it was really that manifoldy.